Thanks for watching the screencast. This screencast is all about slope and rate of change. And our objective for the screencast is that learners will be able to determine the slope of a linear function. So the rate of change is a ratio that compares how much one quantity, which we call the dependent variable, changes relative to another quantity, the independent variable. And for linear equations, we usually call this the slope. And you've probably seen the expression here at the bottom of the screen many times before. What you may not be familiar with is this notation here. These triangles here are the capital Greek letter delta. And when you see the capital Greek letter delta in reference to anything in a math or science class, it usually refers to change. So you really could read this expression like the change in y, which is that dependent variable, divided by the change in x, the independent variable. The independent variable is the thing that we usually can control or change, or watch it change. Time is often the independent variable, rather. The dependent variable is the thing that we're wanting to measure, the thing we're wanting to watch or track, the thing that depends on the dependent variable, the independent variable, rather. So this expression y sub 2 minus y sub 1 is simply the difference of two y values, two output values, two values of the dependent variable, and then x2 minus x1 is those same two corresponding values for the independent variable, change in x. We're going to do three different types of examples here, and these are all fair game to ask you about in our Algebra 2 class. Find the average rate of change. What I think might be one of the trickier things for students in Algebra 2 to comprehend in this type of problem is which of these two things in this scenario where we're measuring the elevation of the sun at a given time, which of those is the independent variable? Which of those is the thing that we that we can control or watch change? In this case, that's time. This is the independent variable. The dependent variable, or in other words like our y, is the elevation of the sun. In this scenario, if we're recording the elevation of the sun in degrees at given times, we're not trying to measure what time it is by looking at the sun, although I suppose if you were really talented you could. We're trying to determine what the elevation of the sun is depending upon what time it is. So to find our slope, our rate of change, we need change in y over change in x. Now, it has not been mentioned yet, but this is probably a good time to mention it. In a scenario in which these two quantities have a linear relationship, it won't matter which two ordered pairs you pick to work with. I don't think this necessarily is a linear scenario. So I just need to pick two ordered pairs that best represent the overall trend. So depending on the ordered pairs you pick, you might get a different answer than I'm going to, and that's okay if that happens. For an assessment, we may very well ask you to pick two certain ordered pairs. I think I'm going to pick these two. I'm going to pick the second one here, and I'm going to pick the very last one. And if you picked different ones, you'd get a different answer than I would, and that's okay. The change in y, then, would be something like 84 minus 26. The order you choose to do this in does not matter. If you'd written 26 minus 84, then you would get a different sign on your delta x as well, and we would get the same answer. For a change in x, since I did 84 first, I'd better do 11 minus 8. All right, 84 minus 26, I got 58. Might want to check my math there, but I think I've got it. 11 minus 8 is 3. I get 58 thirds. That doesn't divide nicely. You could say that's 19.3 repeating if you wanted to. You could also leave it like 58/3 if it doesn't reduce. What I would like to see in a problem like this, though, is units as well. So what did y measure in? Y was the elevation of the sun. That would be degrees per, and then what did the independent variable measure in? That's, I suppose, time in hours. That would be degrees per hour. And that should be on your answer regardless of whether you use the fraction or the repeating decimal. Here's an example, and so is the next one as well, of how you're more likely to have seen this in or practiced this in an algebra class. Certainly did a lot of this in Algebra 1. You probably even reviewed this again in geometry. Find the slope of the line that passes through these two ordered pairs. I've always found it helpful, although not necessary in all cases, to label my ordered pairs. So if this is the point I'm calling point 1, we'll go x sub 1 and y sub 1. We'll call this x sub 2 and y sub 2. And that makes it a lot easier to use the slope formula, delta y over delta x, because now you know what your y1 and y2 are. And it's pretty easy to look back and see what x2 and x1 are as well. So y2 minus y1 would be something like 5 minus negative 1. x2 minus x1 would be negative 4 minus 2. And again, if I had labeled those points differently, if I'd called this point here point 2 and this point 1, again, I would get the different order on both the numerator and denominator, and we would actually end up with the same answer. So 5 minus a negative 1 is actually 5 plus 1, or 6. Negative 4 minus 2 is negative 6. And that, I hope you will reduce or simplify your slope. 6 divided by negative 6 is negative 1. Slope here is a negative 1. Here's a third way in which I hope you are used to experiencing slope. We'll give you the graph of the line and ask you to find the slope. Since it is a linear equation, the slope should be the same between any 2 points you pick. So what I want to recommend you do is just find 2 points that appear to have really nice ordered pairs on the line. Like this one right here. It looks like it's at about negative 2, negative 1. And perhaps I could use 1, 0 as well. Okay. Now what you could do, if you identified those 2 pairs, is you could write out the 2 ordered pairs, and then you could work this problem almost exactly like the last one. And that's not a bad way to do it. I'm going to try and do it just based off of the graph. Between those 2 points, how much did y change? What's delta y? Well, it went up 1. See that it started down here at y equals negative 1. By the time we're at this point, we're at y equals 0. So my delta y is a positive 1. On those same 2 points, how much did x change by? Well, we started here. We went over, I believe, 3. We increased by 3. So positive 3 is my delta x, and I get a slope of 1/3. What I hope you can see, and I'll quickly kind of detail for you as well, is that if I had picked this point here at negative 2, negative 1, and this point at 4, positive 1, I could have gotten different delta y and delta x, but ended up with the same slope. I'd have gotten my delta x to be 6. I'd have gotten my delta y to be 2. And if I had calculated the slope for those 2 points the same way, delta y is 2, delta x is 6, and 2/6 is the same as 1/3. So if you're working with a linear equation, a linear function graph, as long as you pick 2 points around the graph, we should end up with the same slope. Time for you to try this on your own, Panthers. Hit pause. Try to find each slope or rate of change in this scenario, and when you think you've got answers that work, hit play and we'll check it out. On A, it doesn't really matter which 2 points you pick, but I hope you'll pick ones that are easy to spot out here. I'm going with 3, 0, And I'm going to go with 6, 4. And I'm just going to use the graph and try and figure out my delta y and delta x. From these 2 points, it looks like I could go up 4, or like a delta y of positive 4. And then my change in x would be positive 3. So I'm going to go with a slope of 4 over 3, 4/3. In B, we're dealing with a scenario, and the instructions aren't there, but I hope you figured out from context that we're counting a time after we started tracking the time and how many vehicles have traveled through a tunnel. And here again, if we don't know if this is linear, you might get a different answer than my answer if you pick different ordered pairs than I did, but I'm going to pick these two. And I'm also going to say that in this scenario, the time is the thing that would be the x thing, the independent variable. And the thing I'm counting or tracking, how many vehicles have come through the tunnel, would be my y, my output. So my slope here, my rate of change, delta y over delta x, will be something like the difference of my two y's, 2,970, minus 2,131, all over that my change in x, 22 minus 11. So 2,970 minus 2,131 is going to be, let's see, 639. Does that sound right? Oh, not 639, 839. That happened in real time, folks. Quick check. Add that back, 839, I get 2,970. Yes, okay, that works. Bottom's easier. 22 minus 11 is 11. In this particular problem, leaving this as a fraction doesn't seem to be a great choice because it doesn't really describe what we're looking for. How many vehicles is 839 elevenths? Kind of hard to tell. I'm going to use the calculator and divide that out. I got 76 point, looks like 27 repeating. Okay. A little more than 76, and what would the units be? It would be vehicles per minute. I don't have room. I'll make room. Vehicles per minute. Thanks for watching.